Hello, my dear students. Now we reach the last chapter in our optical system course. Now our chapter is under the title of Gaussian beams. This chapter will be delivered, inshallah, across two successive weeks. We will start with week 10 this week by the first part. Actually, it's something like maybe 70% of the lecture, which is directed about the title of the lecture, which is Gaussian beams. And then in week 11, which will be our last new content teaching week, we will finalize our course by what's called the ABCD matrix. So now let's start our lecture with the title Gaussian beam. As usual, I will move between this lecture slides, and also I will sometimes, or actually many times to be honest, I will refer to the lecture script. Of course, as usual, my dear students, both the lecture script and the and the and the lecture slides both are available. I believe you can now see the lecture script. So this is the lecture script. So you can we can use it many times, and also we will use lecture slide as well. So let's start the lecture, my dear students. Now let's start the Gaussian beams, and I will start with the lecture script. Okay. Usually, or we agree from day one in this course about the duality property of the photons, and we say that photons is a particle which include an energy, and this is a definition. For example, we use this definition when we deal with the photon lifetime, for example. So we treat the photon as a particle, and in many chapters, or in many portion of the course, we deal with the photon as an electromagnetic wave. If you remember, in the optical cavity, in the beginning of the optical cavity, we first write the equation of the electromagnetic wave, or of the electrical field inside the cavity, which represent the motion of. So we should now understand this duality property of photon. And as far as photon is a wave, so we can apply the main wave theory on the photon. And I believe you 100% know that one of the main theories applied on the photon is, or on the electromagnetic waves in general, is Maxwell's equation. So basically, in general, in order to find an electrical field and a magnetic field for any electromagnetic wave, you have to go to Maxwell's equation and solve Maxwell's equation under certain boundary conditions. Then you will get the E and the H. You did this in the electromagnetic course, you did this in the microwave, you did it in the antenna, and now we are going to do it in the optical system course in order to understand the phenomena of light. So basically, we can say that div E equals to 0. If you remember, the origin of this equation is that div D is equals to rho V. And as far as we are talking about a free charge region, because normally light is propagating in air, so air is a free charge region, so rho V is equals to 0. And you can say that for an isotropic medium, that D equal epsilon times E, and epsilon is a independent dimensional parameter. Again, if the medium is an isotropic, I mean that epsilon r are not function in x or y or z. That's why you can say simply that epsilon or div E is equals to 0. So it's a simplified form from the original equation, which is div E is div D is equal to 0. So the simplified form is that div E is equal to 0 when you have a free charge region and when the system is an isotropic. The other equation, which is a standard equation, which is that div H is also equal to 0. So knowing these two equations, these are our starting equations. So, and based on your understanding in the microwave course and in the EM2 course, you know that this E is basically a three component. We have an E in the X direction, E in Y direction, and E in Z direction. So we can call it EX times X cap or I, EY times I cap or J, Ez times z cap or k, if you remember. And usually we consider our direction of propagation to be the z direction. So if we consider our z direction as, or if we consider the z direction as the direction of our propagation, then you can say that we have two types of electrical field component. You have what's called the longitudinal component, or the component in the z direction, which is the direction of propagation, and you have two other components, which x and y, where we can merge these two components under the name of the transverse component. I believe again that you hear this word before in the microwave maybe, or in maybe in EM2 as well. So this is the transverse component, which is in the direction not including the direction of propagation, and this is the direction of propagation. So so now we divide this term E into div E equals div transverse times E transverse plus partial per partial Z, which is the div component of the Z times Ez is equals to 0. So this basically this equation is the division of this equation. Okay, now we know the Ez component because we already know that when you are dealing with direction of propagation, the electrical field is varying in the term of e power minus j k z. And I believe that we already use this term, if you remember, while we are studying the optical cavity. And we actually reach the transmission equations, the conditions for maximum, and all these stuff, we do it starting from this equation. So the that component is known. It's an amplitude multiplied by a variation in the phase, which is e power minus j k z. Again, now I'm assuming a lossless medium. There is no alpha, there is no attenuation, and also there is no amplification, because if you remember, we deal with an amplification systems or amplifying materials before. So this is actually just a change phase, a phase changer. So by moving inside this material in the z direction, the phase of the photon is changing by this amount, which is e power minus j k z. And you know that k is equals to omega n over c, or 2 pi n over lambda node, where n is the reflective index and lambda node is the wavelength propagation across the area. So now you know now you know E that. Now you know the component of the that. So you can easily substitute in this equation to get partial by partial z. Simply, this is the constant, and the differentiation of the exponential term will give minus jk. So you will have minus j k, which is 2 pi n of lambda naught times Ez. So this is simply the differentiation of the Ez with respect to the z component. Now let's turn to this element, which is the gradient, or sorry, the divergence, the div transverse times e transverse. Now we need to understand this. Actually, in order to make life easy, here we use a not so widely known mathematical approximation. This mathematical approximation, actually, let me first start to mention a very important point. It is very easy to convince you that when light is propagating, it's propagating in a form of spotlight. So let me now shift to my yes, it's this one. Okay, so now I believe you now see the PowerPoint slide. This is the first slide, actually, just the cover slide, but I will use this figure. I will use the same figure in the cover slide to convince you with a very important issue. What is the very important issue actually is that light is propagating in a form of a spotlight that I can read. So light form a circle. Basically, when you have a laser pointer, when you have a lighting, any type of lighting, and when you direct it to a wall, you will find a spot of light. So usually light is propagating in this form. Accordingly, it's better to describe the system in a cylindrical coordinate rather than in a Cartesian coordinate, because in the XY plane, if you assume that this slide, this is the wall, and that you assume that the wall is an XY, then it's easily to express here this XY in terms of R and theta, which is the cylindrical coordinate, which is R, theta, and Z, or R, phi, and Z. So now it's more easy to make it cylindrical, okay? And then when we make it cylindrical, there is a very not so famous approximation says that the derivative of this R and phi is equals to the same function, which is E transverse, multiplied by D, where D is what we can call the beam finite diameter. It's the diameter of the spot. It's the diameter of the beam. Actually, this derivation is implemented in more detailed manner in Verdine. You can go and try to understand it mathematically if you would like. However, from our perspective during this course, we will deal with it as a fact, just to avoid entering in a huge mathematical details. But you can go to Verdine and you can check this derivation. So now we got the two components. First, the Z component, we have now its derivative. And for the transverse component, we assume its derivative. So simply you can now return to this equation and substitute. Here you will remove diff transverse E transverse by the term E transverse over Z. And you can remove partial by partial Z E Z by this term, which is minus J2 pi n over lambda naught times Ez. And this is, of course, is equal to 0. Now you can have a relation between E transverse and Ez. And as far as we are not interested in phases, I will get the absolute of this result of this equation, so that I will get rid from this negative return by getting the absolute of these equations left and right, and then you reach this equation, which is Ez equals to lambda naught 2 pi n d times Et. Okay, simply until now it's something like some mathematical shuffling in order to get a relation between Et and Ez, but what is the physical meaning of this relation? This is the important question by these things. So now let's try to examine this term, which is lambda naught 2 pi n d. Okay, lambda naught expresses the wavelength of light. We know that the wavelength of light is varying from something like an 0.2 micrometer if it's an ultraviolet light, till we reach something like an maybe 2 micrometer, which is the infrared. So it's something in the micrometer, maybe some micrometer range. So, for example, if you take a visible light, you can say that it's 0.55 micrometer, for example. So the denominator here is in the micrometer range. Okay, what about the denominator in this equation? 2 and pi are constants. N is a refractive index, which is 1 point something, maybe 2, maybe 3, which is some digital number. Okay, and what about D? D is the diameter of the beam. Usually this beam diameter is recognized by eye. So its diameter may be something like centimeter, like millimeter, something like that. So now you can imagine that the denominator of this equation is in the micrometer range, which is 10 power negative 6, while the denominator of this equation may be in the 10 power negative 2 range. That means that this fraction will lead with a number which is something times 10 power negative 4, for example. Okay, then that means that Ez is 10 power negative 4 smaller than Et. In other words, if you can say that you have an electric transverse component, for example, of 1 voltage per meter, the Ez component will be 10 power negative 4 voltage per meter. 10 power 4 reduction. Accordingly, we can say that we can ignore Ez with respect to Et. Yeah, Et is much greater than Ez. This equation stands that Et is much greater than Ez. Or we can say that, yeah, roughly Ez is equal to 0. Okay, let's turn now and ask, do we know a type of electromagnetic field where you have no electrical and magnetic field component in the direction of the propagation? Yes, it's what's called the TEM waves. If you remember the definition of the TEM, or the transverse electromagnetic wave, are those waves which doesn't have either electrical field component or the magnetic field component in the direction of their propagation. They only have electrical and magnetic fields component in the transverse directions. That's why they call the transverse electromagnetic wave. So now, by proving that Ez is very, very, very small with respect to Et, and you can basically do the same using this equation, which is div h is equal to 0, you can do the same to prove that Hz is much, much, much smaller than ht, then you can say that you can ignore the is that and h that components. In the basic one, in the basic optical books, if you go to, for example, to Max Born, which is a book published in 1923, it's a 100 years book, 100 years um old book. They they call this as a quasi TEM wave. It's not a typical TEM wave because you have EZ. Actually, you have an EZ component, but it's a quasi, it's a semi, it's something tends to be a TEM wave. So this definition or this mathematical proof lead us to a very important conclusion that light can be considered as a TEM wave. But here you have to mention a very important point. Light can be considered or should be considered as a quasi TEM wave if and only if the beam diameter is much greater than the wavelength. Because in some very high power coherent lasers, where you have a spot size or a beam size or a beam diameter, I'm sorry, in the micrometer or maybe in the nanometer dimension, this equation will not be or will not get the same results. Because as far as the D is in a micrometer and the lambda is a micrometer, now ET and EZ are comparable, and you will not be able to consider your light as a TEM wave. So, considering your light as a TEM wave is limited to a condition or to assumption that your beam width is much greater than the wavelength of your light. This is very important, my dear. So now we have an electromagnetic wave. We can assume a TEM quasi-transverse, and then you can do a lot of mathematics, which I will not ask you to understand. If you would like to read it, of course, you have the opportunity to read it, but you will do a lot of mathematics till you reach, if you remember, what we can call the wave equation. I believe you do something like that, or you did something like that in the microwave course, and then you solve this equation. As you know, while we are solving Maxwell's equation, usually our unknowns are the E's and the H's, the electrical fields and the magnetic fields. Now we will reach, after solving the equation again, the solution, the exact solution of these equations is not required by you mathematically. Now we will reach this equation. This equation represents the electrical field in terms of x, y, and z, as you can see. This equation is the exact solution of the Maxwell's equation after assuming a quasi TEM wave in the case of light propagation, where Ez is much smaller, is much, much, much smaller than Et. The most important part in this lecture is to try to understand this equation. This is a very general and very important equation in the optics. But let us now first start to divide this equation into portions. We will start, actually I already did this by coloring each part with a different color, but what we are going to do now is that we are going to divide the equation into portions, and we will start to understand each portion individually. Okay, as I mentioned, now we would like to understand the electrical field equation by understanding each term, and as I mentioned, we will portion it into some terms, and then we will try to understand each portion individually. So, how shall we portion it? How shall we portion this equation? Now, if you recognize this equation, you will find that you have an amplitude and the three exponential terms. But two of these three exponential are e power minus j. And as we know mathematically, and I believe you already know that e power minus j is an indication for a phase change. So the green term and the blue term are a phase change in the electrical field. While in the first exponential, which is still in the red, it's e power minus a value. So it's a basic attenuation curve. If you remember e power minus alpha x, for example, it's an attenuation. So this term is an exponential, but it contributes to the amplitude because it's attenuating the amplitude value. That's why we will call all this red portion of the equation as the amplitude of the field. Now, we have two exponential terms with the e power minus j, which indicates a variation in the phase. But the green term is function in z and only z, while the blue term is function in r. That's why we will call the green term as the sorry, as the longitudinal phase, because this phase it changed by change the longitude direction, which is the direction of propagation, which is that. While we will call the blue term as the radial phase because this phase changed with radius. So overall, the electrical field is divided into three sections. We have the amplitude term, we have the longitudinal phase term, and we have the radial phase term. Okay, I will be more and more interested with the red portion, which is the amplitude term. I will give a very quick view for the radial term, and I will totally ignore the longitude term, and I will not ignore it because it's important, because it's not important, but because mathematically it's a bit difficult as it contains a tan minus one function. So in order to describe it mathematically or by drawing, it will be a bit difficult, but I will give the simplest one, which is the amplitude, and then a few maybe overview over the radial. So let's start with the amplitude. This is a very important term that we try to understand. Now let me please return to my lecture slides, which again you can find it also in the e-learning. So let's now shift to the lecture slides. Okay, I believe yeah. Now you can see my lecture slide, and I will turn on my pointer. Okay, now it's working. So this is of course I forgot to mention that this is in chapter 3 in Verdi. This is the equation we did it together, and this is the condition where we say that it's nearly TEM. This is the three equations I just mentioned, the three portions of the equations. And now I'm going to show you, or we are going to try to understand this term, which is the amplitude term of this equation. So let's start to do it. I will use this equation. Okay, so here, as you can see, this is the amplitude term. And if you observe the amplitude term, you will find that this amplitude term is a function in Z and R. So it's a double function. It's a function in Z and function in R. To try to understand it, we have to first make one parameter constant and vary the other, and then repeat the process with make the second parameter constant and vary the first. So in order to make it easy, I will start with the origin of the line. I mean, I start with Z equals 0. Now, as you can see, this amplitude term is function in omega of Z, where omega of Z is given by omega node square times 1 plus Z over Z node over R square. So if you put Z here is equals to 0, that means that you will have omega square equal to omega node square. So this fraction will tend to equal 1 because it's omega node over omega node. And this fraction will have e power minus r square over omega node square. This is simply when you put Z equals to 0. Now, when you have Z equal to 0, you will reach a function only in R, which is E equals E node times e power minus r square over omega node square. Omega node is constant, E node is constant, and the function is only in R square. So it's e power minus r square. In order to plot this equation, it's a very easy exponential equation. If r equals 0, you will have e power 0, and e power 0 is equals to 1, then e equal e node. If you have r equals to infinity, then you will have e power negative infinity, which is equals to 0, then the electrical field will be totally equal to 0. So if I go to plot this equation, so please recognize only this curve. This curve is the plotting. Here you have the r-axis, the transverse, and here you have the electrical field axis. The electrical field axis is equal to E node, or 1 if it's normalized, and then it's go exponentially to 0 left and right because it's E square, so it's gonna go exponentially equals to E0 left and E0 right. So this is simply the first graph. This graph is when when Z is equals to 0, then you have a function between the E and the R, and then you can plot this function in this way. Okay, we have a very interesting point here. Again, the equation now is E equal E node. This term is equals to 1, e power minus r square over omega node square. What if r is equals to omega node? Then you will have E equal E node times e power minus 1, which means that you will have a reduction by e power minus 1 over or 1 over E of that E node value, which is a normalized value here is equal to 1. So this occurs when the radius, which is this is the x-axis, or now it's actually the y-axis, the vertical axis. When the radius is equals to omega node, now you will have e power minus 1 of your magnitude value. So you have a reduction by 1 over E of your magnitude value. This happens when R is equals to omega node. Okay, that's great. That's very great. So this is the first step. We plot a curve of R under Z equals 0. We find that the magnitude is equals to E node at the center. And with the radius of omega node, your magnitude will be reduced by a value 1 over E. These two very important equations, please recognize or please memorize. Now, I will return back to this equation, but I will change my Z. In the first stage, I'll put Z equals to 0. Now, let's put Z equals to Z node. What is Z node? It's just a dummy variable. It's equal to Z node. Okay, so when Z is equal to Z node, that means that this term will be equals to 1, and then that this omega square will be equals 2 times omega node square. Then you will have omega equal root 2 omega node. Then This E node will be multiplied by omega node over omega node times root 2. Then it will be E node over root 2. Then we have E node over root 2. And here we have e power minus r square over root 2 or 2 omega node square. Because I will remove omega square and I will insert it 2 omega node square. So now you are going to plot this curve. Then you will say when r is equal 0, okay, when r is equal 0, then e power 0 is equals to 1, and then you will have e node over root 2. So please recognize, when z equals 0, you have a maximum magnitude of e node. When z is equals to z node, your magnitude becomes e node over root 2. So a reduction in the maximum magnitude. This is the first observation. Then your equation now is E equal E node over root 2, e power minus r squared over 2 omega naught squared. What value do you need to reach this exponential to be e power minus 1? You have r squared over 2 omega naught squared. Then you have to put r squared equal to omega naught squared, or you have to put r equal to root omega naught. Let's now do it in the graph. So when you reach a point z equals z naught, in order to reach the same value, which is e power minus 1, you will have to put a value which is root 2 omega naught. In the previous case, when z equals to 0, the value was omega naught. Now the value is root 2 omega naught. That simply means that when you make a change in the z, when you move in the direction of the propagation, the amplitude of the peak signal decrease from E node into E node over root 2, and the width of the signal increase from omega node to root 2 omega node. This is simply this shape, my dear students. Whenever you have a light source, and this light source, or the distance between the detector, which may be a wall, and your light source, whenever the distance increase, you got a wider spot light with a lower intensity. Whenever the Z increase, your spotlight intensity decrease, and your signal or your width or your diameter for the light beam width increase. This is a very, very important observation of what we call the Gaussian beams. Actually, we call it the Gaussian beams because we have here a Gaussian distribution, something like a Gaussian distribution of the light with respect to the radius. As you can see, that's why they call it the Gaussian beams. So the Gaussian beams is basically the relation between the intensity of the light and the light distribution over the diameter or the area of the spot size. As the distance of the propagation of the light increase, its intensity decrease, but its distribution area or the diameter of the spot size increase. So this is the main important observation in this manner. Okay, now let's go to the next step. As I mentioned earlier, I will give a very important focus on this. I will ignore this because it's very, very hard mathematically, and I will just show you a concept related to this, which is the radial phase. What about the radial phase? Okay. The main and the only important information I need you to keep in your mind regarding this radial phase is that simply the phase is function in the radius. That's very simple like that. When a phase is function in the radius, that means that the wave is propagating with a radial or a phasor or a phasor phase, not a planar phase. Okay, I believe that in this point up to now you did not catch what I need to say, or you can ask a question. Where is the problem? Okay, the wave is propagating in a radial phase, not in a planar phase. Where is the problem? Okay. Let me answer this or try to answer your question or the questions that I believe that it's your in your mind using this. Now I believe that you now see my whiteboard, I think. Okay. If you remember, we deal before with what's called the optical cavity. In the optical cavity, my dear student, I was assuming that I have two mirrors. This is the first mirror, for example, and this is the second mirror, for example. And I assume that these mirrors, the light is going to propagate and reflect between these mirrors. That's pretty very. But in this study, I was dealing with the light as a particle, and also I am dealing with the light as an electromagnetic wave, if you remember. And we say that the phase of the we say that the phase of the of the electromagnetic field, which is or the electrical field, which is a photon, it changes with the distance. That's why we put the term e power minus j k z. And with a round trip, we say that it's e power minus j k 2d. That's perfect. But now the phase is not only changing with the distance, but it will also change with the radius. Then we can assume that the phase front, maybe you hear this word before in the microwave, we can assume that the phase front of the signal is something looking like that. I will try to make it in a better manner. I'm not so good in drawing, so please accept my apologize for that. So let me first start to write. This is the wave. This is sorry the mirror, and now this is the so the wave is propagating in this manner, and the mirror is flat. That means that not all the wave will touch the mirror at the same time, because here your wave front is in radial format. It's function in radius. So you will have first this point reach, and then this, and this is, and then this. Then you have an accumulating delay due to this interaction. To make it more and more clear, I can ask you a question which is very far from this topic. Why do you think that curved monitors or curved screens are more familiar to the human eye with respect to a planar screen? It's simply something related to the retina of the eye. When your eye retina have a certain curvature, the screen is implemented with the same curvature. So the light emitting from the screen reach your retina in the same distribution that your retina is designed with. However, when you have a planar screen and your retina is curved, then the light is reaching with different delays or with different phases with respect to that. That's mean, my dear students, that let's now turn back to the lecture. Okay, so I believe you now see my lecture. I hope so. And let me now turn the laser pointer again, my dear students. Okay, so that's mean that in order to have an optimum cavity, it is better to have your cavity circuit or curved, not a flat cavity. That's to accommodate the phase change with respect to radius that occurs on the signal. So the screen is designed in the same radius your eye is designed with. We will implement the same. We will make the mirror designed with the same radius the signal is coming with, which is this R variation. So simply, it's a better to make a spherical mirror rather than to make a planar mirror in order to make a better reflection for the signal. Okay, so Basically, we have two mirrors. So simply, you will say that the first mirror will equals to Z1. Z1 is the distance traveled by the photon till it will reach the first mirror, which is Z1. 1 plus Z node over Z1 all square. And R2 equal Z2, 1 plus Z node over Z2 all square. This is basically the radius of the two circles, or the two mirrors, sorry, in order to accommodate the variation of the radius in the mirror, or sorry, in the signal. So now you have to say, or to search for some conditions to design your mirror. We will take here actually 3 cases. Let me now start, or let me return back to the lecture, I think, first, and then I think I will need the whiteboard later, but now let's turn to the lecture. So, okay, I believe there is something wrong. I don't know what it is, but let me make it in another way now. Hope I can. Okay, I think it's now okay. So let's start with the cases, and let's start with case number 1. In order to make these equations more simple, let's assume that R1 is R equals to R2. And how we will make it is that we assume that our origin is at a distance equal to d over 2. So I will now use my whiteboard again, please, my dear student. I'm sorry for all this shuffling, but it's just I need to show you each and every step. Let's now clear our whiteboard. And okay, I will start to plot the mirrors. Forgive me, I will make it flat because it's more easy for me to make it flat rather than to make it curved. But please remember that this is a curved mirror, not a flat mirror. So now we have these two mirrors. This is M1 on the left, and this is M2 on the right. And now the distance between these two mirrors is D. If I assume that the origin point is here at a distance d over 2, then the photon will travel a distance d over 2 in order to reach the second mirror, which is the same distance the photon will travel from the origin, but in the other direction, d over 2, in order to reach the first mirror. So the distance z1 is equal to over d over 2, and the distance z2 will be equal to also d over 2. That's what we are going to do in this case. So now let me return again to the lecture script. And let me again turn my laser pointer. Okay, so now R1 is equal to R2, and Z is equal to R, and Z is located in the origin, so that the distance between the origin and each mirror is d over 2. So by substituting, R equals to d over 2 times 1 plus Z node over d over 2 all squared. This is just a very simple substitution in the basic equation. Now you know that Z node is the distance at which we lose 1 over root 2 of our intensity based on the example we do together. So Z node is a distance, whatever it's the definition, but it's a distance, should be real value. If you try to get Z node in one side and all other parameters in one side, you will find that Z node is equal to d over 2 to r over d minus 1. So in order to make sure that Z node is a real value, you should have 2r over d all the time greater than 1, so that this exponential has a positive component, not a negative component. Otherwise, Z node will become imaginary value, and actually this is physically not accepted because Z node is a distance. So the condition here is to make 2r over d greater than 1. Again, please, r is the radius of the screen, of the mirror, and d is the distance between the two mirrors. Again, please deal with the stupid terminology over d. It's the third r in our course. First, we take r, which is the reflection of the mirror in the optical cavity shutter. Then we take R as injection rate or the pumping rate in the three-level laser, in the laser electron. And now you have a new R with a new meaning, which is the radius of the spherical mirror. So please usually detect the value with respect to the context. You have to see the context. For example, when I am dealing with Gaussian beams, then of course these are is the radius. It's actually basically can be easily recognized because R is equal to some distances. So its dimension is a distance the dimension. So it cannot be a injection rate or it cannot be also a reflection. So now this is the condition in the first case, case number one, when R1 is equal to R2 is equal to R, and when Z is equal to 0 at a distance d over 2. The second case, when R1 is still equal to R2 is equal to R, and this R is also equal to D. So you manage to make R is equal to D. You adjust R equal to D. So let's say, so D equals to D over 2, because now I put R equal to D. D equal D over 2, 1 plus Z node over D over 2 squared. Here you have a finite value that Z node will be equal to D over 2. So this is an exact value for Z node, that Z node is equal to D over 2. So another system, when you put the origin in one mirror. So now let me return. Let me return to this. Okay, let me now return to my whiteboard. So in this system, it's somehow one of the advanced systems. You have something like that. You have a flat mirror in one side, and you have a curved mirror in the other side. Your origin here, this is your origin. So when the wave reaches this signal, or this mirror, sorry, it will cover a distance called D, which is the distance between the two mirrors. So you have a plane curved system. So now let's turn back to our lecture script. And again, let's turn on our laser pointer. Okay, so I think it's not well working. Don't know why, but okay, now it's working. So now you have a plan curvature system. One side is plan and one side is curvature. So R, the radius of the curve, is equal to D, the distance, plus 1 plus Z node over D all square. So Z node equals to D over R over D minus 1. Again, in order to make your system stable, in order you have to make a real system, you have to make Z node real value, then you should have R over D is greater than 1. So now it's very easy. Whatever the system is, you just start with this equation. Based on the assumption, you solve the equation in order to get Z node. Either you will have a condition for Z node, like the case number 1 and case number 3, or you will have a finite defined value for Z node, like the case number 2. Okay. My last point in this lecture is again related to the optical cavity. Now we will reach the most general equation for an optical cavity. If you remember, first we say that the surviving factor in the optical cavity is R1 times R2. When it's a lossless optical cavity, no gain, no loss. And of course, we neglect the phase propagation because, as I mentioned, we deal with the absolute S or the absolute of the surviving factor. If you have a gaining factor, then we multiply by e power 2 gamma d, where gamma is the amplification coefficient. I think we deal a lot with gamma, either in chapter 1, chapter 2, or chapter 3. So now we have an amplification, then whenever the signal is propagating, the number of photons increase by the factor gamma. But what if you have a gaining factor and an attenuation at the same time? Then this is the general equation. R1 and R2 are the losses in the mirrors. E power 2 gamma d is the amplification term, and e power minus 2 alpha d is the attenuation term. So now you have a new gamma equation. If you remember, the previous gamma equation was without this alpha term. Now you have an alpha term. So now you have to set your amplification to dominate on the reflection of the mirrors from one side and the attenuation of the medium from the other side. So this is a very basic equation. To make it simple, we put R1 is equal R2 equal R. So now this turn into ln 1 over R, and I multiply by D. So we have gamma D equal alpha D plus ln 1 over R. When R is very, very large, I mean when R tends to 1, you can say that ln 1 over R is approximately equal to 1 minus R, which is transmission. So we can say that gamma D equals to alpha D plus transmission. Now you know that gamma equal gamma naught plus 1 over I over mu time over IS. This is the famous equation we reached in the previous lecture in order to assume or in order to understand that the gain is saturating gain and not propagating till infinity. So you can say that 1 plus I over IS equal gamma naught over gamma, or I mu or the intensity equal IS times gamma naught over gamma minus 1. If you multiply these two terms by D up and down, and then you have gamma naught D on the denominator, you already have an equation for gamma naught D, which is alpha D plus D. Then you substitute it here. Then you have the intensity is equal to the saturation intensity multiplied by gamma naught D over alpha D plus T minus 1. Okay. In order to make this equation, as you can see here, this is the transmitted intensity. The transmitted intensity is equals to T times the intensity. So this is the intensity inside the cavity. What will be transmitted is T times the intensity inside the cavity. So what I make is now I transmit T times this term, and then I will find the value of T at which this is maximum, the intensity is maximum. Then I will make partial I applied by partial T equals to 0. Then I will get this equation, which is T equal minus alpha D plus root gamma naught T. So if the transmission value is equal to this value, then you are maximizing the output intensity coming from or getting from the cavity by this equation. This is very simple mathematical issue. Now, in the next lecture, which will be our last lecture as a new content, after that we will continue only by revising and solving problems. In the next lecture, my dear students, we are going to make what's called the ABCD matrix. The ABCD matrix is actually something like the S matrix in the microwave, where you are trying to represent your optical device in a matrix which relate the inputs and the outputs. We will try to understand how we can construct an ABCD matrix for a lens, a mirror, or whatever the output is. So thank you very much, my dear students. Waiting for you in the next lecture, which will be, inshallah, the last lecture in this course. Thank you for your concentration, and see you later in the next lecture, inshallah.